بالتالي المحاضرة هاي ممكن بس تخلص تلاقيها موجودة برضو على الإي-ليرنينج. You can view it, you can download it. ما في مشكلة. So I will start by taking any question if you have so far على اللي أخذناه، وتحديدا على آخر إشي حكينا فيه إذا بتتذكروا which was حكينا عن الانبوت اوتبوتس والبنز اللي موجودين بشكل عام في المايكرو كنترولرز، وتحديدا بالاتش سي اس 12 مايكرو كنترولر. حكينا how to use these input output ports, how to configure them using assembly language. So if you have any question, please ask it now. Otherwise, I will proceed and share the slides with you. Okay, can you see the slides now? Okay, I'm just trying to figure out how to get the chat. Okay, so everybody is seeing the chat, the slides, مظبوط. Okay, so I will. Okay, so as I said last time, we started to discuss the input-output ports, which are very important in embedded systems and microcontrollers. So we said the HCS12 microcontrollers, they are very rich with input-output ports. For this table shows the ports, the names and the number of pins associated and the names of these pins. And as we saw last time, when you refer to these pins and ports, you usually use the names instead of the addresses and the bit numbers, the pin numbers, which will be included in the which are defined in the include file that you put in your program. Okay, so this is what we covered last time: how to output some value, how to output some value, how to use an adequate directive to define it. But you don't need this, as I said, because it is already included in the header file that will be added to your project in CodeWarrior once you create the file. Configuring the direction, as we said, each port in any microcontroller, each port is the operation of each port is tied with two registers. One is for configuration or control, which we call the direction register, and the other one is the data register, which holds the input or output data depending on the state of the associated pin. So in our case, for example, port B, we have DDRB, which is the direction register register for port B, and we have PTB here, for example, which is the data register for port B. Of course, each of these registers has an address, but we refer to them using, as we said, the names. It is much easier. These are the ports. This is a note on the push buttons available on the Mini Dragon. Not all the boards that I have these push buttons, though I will not discuss it. If you need to use push buttons to interface push buttons to the microcontroller, just use external ones and connect them to the pins. We also talked about how to interface simple output devices, and the simplest output device ever is the um, light emitting diode. We discussed how to interface it. You can connect it either, you can connect the pin to the anode of the LED, and in this case you need to output logic high in order to make it turn it on, or you can connect it, you connect the port to the cathode, and in this case you need to output 0 in order to turn it on, and this requires the anode to be connected to VCC. Different arrangements. The point here is it doesn't make difference for microcontrollers made of CMOS, because the maximum source current and the maximum sink current are equal. This could be an issue when we work with TTL devices, because with TTL devices, because the sink current and source currents are different. Usually, as we said, we might need to put a buffer when we connect, in general, any device, to form kind of protection to the port in case we sink or source too much current. We can protect the pin. This was an example how to connect a set of LEDs and control their operation. The LEDs are essentially connected to port B, and what was required is to write a program to make one LED on at a time for a certain amount of time, then move to the second one in this direction, then move, goes up in the other direction, and keep doing this forever. And that's why as we discussed in the class, you need to write an endless loop in your program, which is the case for all embedded systems. Usually you do the same tasks over and over. So this was the program. This was the forever loop. And inside that loop, there is another loop which moves, which turns one LED at a time, then it delays for some time and does that, and this internal loop executes 16 times, and in each time we output one of the patterns available in this table. And basically, if you look at them, there are 16 patterns. Each of them corresponds to lighting one LED in the forward direction and the same LED in the backward direction. Now, for the last two lines, I did not talk about them last time, but these are required when we develop our program using Code Warrior. This code was written using Mini IDE, which the book uses it most of the time, but we will use Code Warrior. So if you want to use Code Warrior, you need to uncomment these two lines. And effectively, when you add a new project in Code Warrior and you add the main assembly file, the template will by default include these two lines in your program, as probably Muhammad told you in the tutorial. Then we talked about interfacing to 7-segment displays, and we know that 7-segment displays are essentially LEDs, 7 LEDs, and usually we have a decimal point here. Sometimes they are common cathode, sometimes they are common anode, and the interfacing is just straightforward. Here we have the buffers. 244 is the hex or oct buffer. 8. This chip has 8 octal buffers. The most important thing about 7-segment displays comes when we talk about interfacing multiple of them, and this puts a huge pressure on the number of pins that we need from the microcontroller. So one way around this is basically to share or to multiplex the pins between multiple displays, and in order to deceive the eye of the human, basically we turn one of these displays at for a very short amount of time, display the digit, then turn it off, move to the second one, display the digit, turn it off, move to the second one, turn it on, display the digit, and so on. This is called 7-segment multiplexing or sharing. And the way we enable and disable these displays is basically by connecting their, in this case, the cathodes to the pins, to another set of pins where we can enable or disable any of them. Here in this case, since this is common cathode, we need to output 0 here in order to turn this display here. We need to output 0 here to turn this on, and so on. Otherwise, if you output 1, nothing will flow here because this is common cathode. And this example here shows how to display 7 on display number 5. So we need to disable this display number 5. So we need to output 5 is connected to PP7, port P, pin 5, I'm sorry, port P, pin 5. So we need to output here 0. We need to output 0, 1, 1, 1, 1, 1, such that this will force all the other displays to off state, and this will be turned on, and then we output the pattern that we want here. And this is what is done by these few instructions. The next thing we discussed was another program to display this on the same circuit shown in the previous slide. So I think we went through the code. So what we did basically is we defined an array, and this array basically contains 16 or 12, yes, 1, 2, 3, 4, 5, 6, 12 bytes, and each 2 consecutive bytes correspond to turning on one of the displays and displaying certain value on it. Then we looped through it as we did in the previous example. Okay, so this is a very quick summary on what we did last time. The next thing that is presented in or discussed in this chapter is generating digital waveforms using input-output pins. So now what we have, what we are discussing are basically the input-output pins, and we can connect different types of devices to these pins. The simplest output device is the LED and 7-segment display. Another output device, which is a simple device, is basically a speaker or a buzzer. For example, we can just bring here. We can, if this is the microcontroller, we can bring a speaker or a buzzer to sound, to output some sounds. And what is this slide? What this slide is discussing is basically producing waveforms on the output pins. For example, on pin A0, we might output something like this, a periodic square wave. Now this, if you feed it through some filter, which is, this is what, a high pass filter or a low pass filter? Who knows? Is this a low pass filter or a high pass filter? Power guys, write your answer. Is this a high pass filter or a low pass filter? It's high pass or low pass? It is a low pass filter because when the frequency of this signal is low, this is an open circuit. When the frequency of this signal uh, is high, this will become a short circuit. So high frequencies will go through the ground. It is low pass. ولا high pass يا باسل. High pass, this is short circuit, high frequency. So it will short the signal to the top. Anyway, so if we pass this through a low pass filter or band pass filter, we can produce sinusoidal or near sinusoidal signal, which can be played on this buzzer. So this is what is presented here. We can, by connecting a pin, to a speaker, we can make sounds. We can make sounds at certain frequency. So in the following slide, this is a program. Write a program to generate a 1 kilohertz periodic square wave. So we want this to be the frequency 1 kilohertz. 1 kilohertz means that the period is one millisecond. The period is 1 millisecond. So in order to do that, we need to output here one for our logic high for 0.5 millisecond, and then logic 0 for 0.5 millisecond. So basically, we need to do this forever. So there will be an endless loop, and inside that loop, we simply write instructions that output 1, then delay, then output 0, then delay, and so on. So this is what we have here. This is what we have here. Originate the program LDS, which loads the stack with some value in order to initialize the stack pointer. And usually you find this in the template that the code warrior gives to you when you create a new project. B set DDRT bit 5, because here we want to use pin number 5 from port T as the output. Then forever we enter the loop. B set this pin to 1, load Y10, jump subroutine 50 microsecond. So there is the subroutine here to delay for 50 microsecond, but we will pass to it 10. So it seems that the subroutine accepts an input value of 10, an input parameter of 10, and repeats the delay of 50 microsecond by 10 times, which becomes 500 microsecond, which is 0.5 millisecond. Then we clear, we do the same, we delay, and so on. And we do this forever. This is very simple and very straightforward. Now, can we think of another way to write this program to make it shorter? Can anyone think? Basically, what we want to do is to change the state of the pin from 1 to 0, and then from 0 to 1 every 5 millisecond. So, or every 0.5 millisecond. So basically, if we start, let me write on the board. Inside the forever loop, if this is the forever loop, if I start by, before entering the loop, I set PTT bit number 5. So initially, before I enter loop, the pin is set high. Then inside it, ILDY hash 10 jump subroutine delay 50 microsecond. Then what can I do? After 50 microseconds or 500 microseconds, I want to change the state of the pin to 0. How can I do that? Like if I write bit clear as it is shown here, then I will always clear the bit, but I want to toggle or to complement. So if I say comp PTT, this will complement the whole data register of port T. So the one that was here, it will become 0. But this will complement the whole port. What if some other devices are connected to pin number 0, pin number 1, pin number 3, and so on? They will be complemented as well. So how can we complement only the bit number 5? Yes, XOR. Yes, Yazan and Muhammad. Yes, we can use XOR. So try at home to, you are at home, try after the lecture to complete this, this other version of the program by writing. I think you need 2 instructions here in order to complement. Then you jump or branch forever. Okay, so basically all what you need to do, think about it. 2 instructions will do the job. Shift instruction, no, Muhammad, will not work. XOR is the choice. If you XOR, yeah, you XOR the mask, Marwan, the mask will be 0, 0. It's bit number 5. We start counting from 0. So we need 5 zeros, then 1, then 2 zeros. Okay, so the mask will be 0, 0, 1, 0, 0, 0, 0, 0. Because this is bit 0, 1, 2, 3, 4, 5. This is bit number 5. Okay, so basically you need to XOR this location, which is register port T with this value, then you store it back to the same location. I think it is EXOR, for example, A, PTT, $ hash, $. I'm not, yeah, think about it, think about it. I will not write it, think about it. It's just another way to think, to write it. Okay. Okay, the next and the last topic in this chapter is basically interfacing an input device, and the simplest input device is a switch. Is a switch, regardless of the type of the switch, whether it is a push button or is a dip switch. It doesn't. Yes, Mohammed, think about it. Okay, so basically we might need to interface the microcontroller with a switch, and this is the switch which can open or close regardless of the type of the switch, whether it is a push button or it is a dip switch. Now if we look here, for example, if it is connected to PB0, port B, pin number 0, if we want to input a 0 or a 1. So if we connect it like this, +5 volt, for example. Now, if the switch is closed and we read this pin, we read a 1 in the PTB register. Specifically, bit number 0 will be set to 1 if we read the port when the pin is closed. However, when we open the switch and read the port, what will be the value inside the port B register? What will be the value inside port B register? You cannot tell, because if you open the switch, this is not connected to anything. This pin is not connected to anything, so the value could be 0 or 1. The value, you will know, you will read some value, but you cannot tell. It could be 0 or 1 because this pin is floating. So the problem here that this switch can define one state, either close or open. It can connect you to +5 volt, or it can connect you to nothing. So the idea here is we need to allow this switch to specify two determined value. So there are two ways to do it. We can use something like this. We can put a resistor here. So now when the switch is open, this resistor is connected to ground, and this pin will be connected to ground, and you will read a 0. When the switch is closed, you will connect to +5 volt, and you will read logic 1. You will read logic 1. So this is very important. We need a resistor in order to define the other value when the switch is opened. Now this resistor will force this pin to 0 when the switch is open. That's why we call it pull down resistor. And usually it is in the range from 5K to 10 kilo ohm. 10 kilo ohm. So this resistor is very important because it defines the input value when the switch is open. Another way to do it is basically, if this is the pin, is basically to connect the resistor here. This is +5, for example, and you put the switch here. And this is just the opposite case. This is just the opposite case. Now, when the switch is open and if you read the port, you will read +5 volt. Now, when you close the switch, you connect this point to ground, and if you read the port, you will read a 0. So this resistor, when you use this configuration and the switch is opened, this resistor has the responsibility of pulling the voltage at this node to logic high or to high voltage. That's why it is called a pull-up resistor. That's why it is called a pull-up resistor. And the same thing, it is in the range from 5K to 10 kilo ohms. This is very important when we are working with what we call single pole, single through switches. This switch, it has a single pole, it has a single path or through the switch. So when it is closed, it can connect you to some value, but when you open it, you are not connected to anything. So this is single pole, single through switch. This might not be a problem if you have a switch that we call single pole double through switch, which is something like this. You can connect it. It has two paths. You can connect to here, or you can connect to here. So for example, you can put here 5 volt. You can put here 0 volt. So this is a single pole double through switch. It is a single pole double through switch. In this case, you don't need resistors. But usually most of the switches that we work with, especially push buttons, and you know the push buttons, those buttons that bounce, you press on them, they change the state. When you remove your finger, they go back to their original place. They bounce back. So these are single pole, single through switches, usually. So most of the switches that you work with are single pole, single through switches. So this is how you connect or interface a switch. What we have here on the slide is basically a set of DIP switches. These are 8 DIP switches. Each of them is single pole, single through switches. That's why we have here pull-up resistors, 10 kilo ohms. So by default, when the switch is open, we read the port, we will always read ones because all the switches are open. If you close any of these switches, the corresponding node here will be connected to a ground, and you read a 0 in that place when you read the port. Okay, any question? All right. So here we have an example to read from this circuit. To read data into accumulator A, configure port A. All pins are configured as input by storing a 0 to the direction register of port A, and then we read the value simply into the accumulator LDA port A. So we will read the values that appear at these nodes into port A, into accumulator A, register, and this value the values will depend on the state of the switches, whether they are open or closed. Now, these are just examples on simple input-output devices: the LED, the 7-segment display, the buzzer, the input, the switches. More complex or more advanced devices are explained in Chapter 7. Specifically, Chapter 7 shows how to display, how to connect to LCDs, keypads, servo motors, digital analog converters, and so on. And this could be very important to you when it comes to working with the projects. You might need to go back to Chapter 7 in order to see how to interface to such devices. Now, what is left in this chapter is basically how to perform debugging, certain advices, certain procedures, how to perform debugging if you are working with subroutines technically. So please go through them, few slides, 2 slides, how to debug, just general advice, and mostly you know how to do that. Okay, so this is regarding Chapter 4, which ends our discussion on using assembly language to program the HCS12 microcontroller. We will come back a little bit and touch a little bit on assembly language in Chapter 6 when we talk about interrupts, but it is just about how to configure and use interrupts in assembly. But all what we need from assembly is just what we discussed in class in terms of instructions and addressing modes. Okay, so I will now go to Chapter 5. Chapter 5, as I said last time, is about using C as the programming language um, for the pick for the HCS 12. Um, so chapter 5, C language programming. It is a very, uh, this slide set is very large. It contains about 100 slides, but most of these slides are examples. Most of these slides are probably you know the content of it. It is a review on C programming language. So I will go very quickly. I asked you last time to do some work and some homework and read these slides. So basically, if you, as you know, any C program consists of functions and variables. The functions, inside the functions, usually you have or you write statements, and each statement specify certain set of operations. And there are different types of statements: declaration, where you declare the variable; assignment statements, where you assign values to variables; function calls; control statements such as if, while, for loop, and null statements. We know the concept of variables in programming languages, where we declare variables to store values during program execution. Any C program should contain a main function, which works as the entry point for your program. Your program may contain, in addition to the main function, as many functions as you want, but there should be a main function in any program that you write in C. And you know this already. This is an example on a C program. We have here include standard I/O for basic input-output operations, integer main. Here you declare certain variables of class of that type, integer A, B, C. You assign values to them. You print the values on the screen, then you return a zero. So probably most of you, or if not all of you, they know how to write simple programs in C. And in this course, when it comes to using C to write, to program the microcontroller, we will write very simple programs. One or two or three functions with some control statements, with variable declaration, and that's it. It won't be that complex programs. Here it tells us what types of variables you can define in C. We have the void, we have the character, the integer, the float, the double. And here it lists what is this data type and the size of that data type. For integers, we can use qualifiers to declare the integer variable as short or long. And the definition of short and long depends on the compiler. For example, if you use the GNU C compiler, short makes the integer 16 bits. So for example, if you say short integer, then it is a 16-bit. And if you say long integer, it is a 32-bit. And for in other compilers, it might be different. Short might be 32-bit, long might be 64-bit. But this is for the GNU compiler. Also, for integers, we can use qualifiers such as signed and unsigned to define whether to specify whether the integer is signed, is used to store signed value or unsigned values. So here are such examples on how to declare. We can define constants in C. We can define strings using single quotes and double quotes. Here, how to specify numbers in different bases. Decimal, it needs no prefix. For example, you write it straightforward. Octal, use 0. So you write it like this. Hexadecimal, which is of interest to us. because it's easier to write values in binary in hexadecimal, shorter and more compact. We write 0x, not $sign. We used to write it as $sign, for example, 3F, but the C compiler uses it as 0x, recognize it as 0x 3F. Okay, arithmetic operations, straightforward: addition, subtraction, multiplication, division, modulus operator, modulus operator, increment by 1, decrement by 1. It depends on the compiler, Yazan, but I think the code warrior uses 0b. The compiler uses 0b, but I will double check that. Okay, 0b. Okay, so these are the set of operations that you already know. Bitwise operations, they are very, very important when programming microcontrollers in general, because through bitwise operations, you can perform operations between a value and a mask, which is very essential, as we saw in configuring the ports and reading the ports. You need to perform bitwise operation, so you can do the same at the high level. This is the AND, OR, XOR, NOT, right shift, and left shift. Example here, the AND operator is often used to clear one or more bits, because if you add a value with 0, it will become a 0. For example here, PTH equals PTH and 0BD. So what we are doing here, we are ANDing register port H, the data register of port H, with a mask value of 0BD of BD. So B is 1011, D is 1101. So essentially you are clearing bit number 1 and bit number 6 in port H. Same thing, the OR operator is often used to set one or more bits to 1. Because if you OR anything with 1, it becomes 1. Here you OR port B with this mask, which is all zeros except the bit number 2, except bit number 6. Yes, except bit number 6. And other bits will be ORed 0. The XOR can be used to toggle a bit, as we said in the last example in chapter 4, when I asked you to modify the program to use XOR. You can use it to toggle the state of the bits. If you XOR it with 0, it will complement. Okay, so shift operations, same thing. This is for shift right, and this is for shift left, which is very important. Same advantages that we discussed when we talked about shift operations and assembly language. Like now, most operators, most arithmetic and logic operators can be combined with the assignment operator for shorter representation. For example, this implies that this is equivalent to PTH equals PTH ANDed with this masked value. The same thing here, XYZ right shift equals 3, which implies shift the variable XYZ 3 times to the right and store it back into XYZ, which is the combined operator. It is a combined operator. Uh, Relational and logic operators, they are very important when it comes to working or writing control statements such as the for loops, the while loops, the if statements. So you need operators to compare conditions, to check for conditions. You need operators to combine conditions. So here it comes the relational operators where you can compare, some value to another value relative to other values. So these are the relative operators. And sometimes you want to combine more than one relative conditions together. So you use and or not. This is very important to distinguish these operators from the bitwise operators. There we had only single and, single or, to indicate it is a bitwise operation. Here it is a logical operator which combines conditions. For example, you can say, if I write on the board, you can say in C, if x is less than 10 and x greater than 0, then do something. So here I need to use double and to indicate that this is a logical operator. It is not a bitwise operation. If you put an and, the compiler may tell you this is wrong, or it may not give you an error, and it will perform AND operation between the value here, and based on that decide if it is 0 or not 0 to execute the if part. Okay, Marwan, then regarding your question, when we perform the right shift or left shift, you are asking where does the injected bit go? Does it go to the CCR? Now, of course, it will go to the CCR because these statements, high-level statements, for example, here, the high-level statements such as this one will be converted to assembly language, to equivalent assembly language, and the only the assembly language, all shift operation, they pass through the carry. Trying to get the chat back. Yeah, so if you write this instruction in Code Warrior, you compile it, then you look at the assembly code, you will find depending on the type of the variable XYZ, if it is signed, it will use arithmetic right shift. If it is not signed, it will use logical right shift. And these two instructions will use the carry to store the ejected bit. Okay, so the following here, these are a few examples on using the operators, equal, relative, and logical operators. Now, somebody may ask here that we are using single and. Of course, we are using this single and. We are not here. We are not combining conditions. We are not combining conditions. We are performing certain calculation. We are ANDing some value bitwise with this mask. Then we are saying if this value is not if this value is not 0, do something statement. Okay, So this is, we are not combining conditions. This is not a condition. This is a mask. So this value is ended with this mask. And if the result is 0, then we will execute the statements inside the if block. Here, yes, we are combining two conditions. This is a condition. This is a condition. Okay, so Marwan, I can't understand your question. What is it? Which one was the one's complement instruction? One's complement instruction computes the one's complement, the com instruction, com instruction. How does your question relate to what I'm talking about? Of course, yes, yes. For example, Amal, Amal asking, all the IO pins are defined in the include instruction, in the include file, yes. For example, this register, I'm sorry, this register is the A to D register status, A to D status register. It is already defined in the include file. So I am referring to it by name instead to refer it by to it by address. Okay, so for Marwan, I will go back to the previous slide. This slide, Marwan. Here. تقدر تحكي على فكرة مش داعي تكتب. Okay. مستحي تحكي؟ Are you shy? Okay. Flow control, very important statements in high-level languages, which correspond to the branch and conditional branch instructions that we discussed in assembly. So as you know, there are many state types of statements. We have the if else statement, if statements, else statement. Now, if the body of the if is only one statement, you write it this way. But if there are many statements inside the if block, you need, as you know, you need to use the curly brackets. You write here curly bracket. The pen is not helping me. You need to write curly brackets to define the block, opening bracket and closing bracket. Okay, so this is a single statement F, single statement else. ممكن we may have F, else F, else F, and so on. Same idea here. Every time there is more than one statement in the block, we need to use curly brackets. And here, what do I mean by curly brackets? This is the switch statement. You need to put curly brackets, then you put the cases, and here we put the value that this expression evaluates. This expression evaluates to. Based on the value here, we have set of cases, and each time we based on the value, we execute one of these cases. For loop, very straightforward. We have a loop counter, or loop index, starting value, end value, and the increment or decrement value. Then we have some statements inside the loop. If there is only one statement, you write it this way. Otherwise, you need to put the curly brackets. The while statement, same thing. While some expression, which define the condition that has to be true in order to execute the body of the while statement. For example, here, while this integer t and t, while this variable is true. True implies it is not zero. So any positive or negative value is considered as true. The body of the loop will be executed. And the only way to get out is to have some statements inside the loop to modify this variable. Otherwise, it will become an endless loop. It will become an endless loop. Do while, same thing. You do some statements while some expression is true. And this is, we already discussed that. This is different from the while statement in the sense that we will always execute at least the one time. Then we will check for the condition. While in the case of the while statement, we check for the condition, then we decide whether to execute the body of the while loop. I will not go through this, the input and output, because this is related on printing the screen, reading values from the keyboard. If you need them during debugging your program, you can use them. But for the microcontroller, from the microcontroller perspective, these are not, these cannot be used because they cannot be translated into actual assembly instruction. But these are useful when you want to see something on the screen. When you debug, when you perform simulation in Code Warrior, you can print on the terminal the values of the variables and so on, or you can input values and store them in registers in the simulator, not in the real board. This is related to output formatting string, and this is not of important to us. How to format the printed value on the screen, how many digits to use for the value, whether it is a string or integer, float, and probably you remember that. These are the formatting specifiers. Important topic here is the functions. And we discussed previously what is the importance of subroutines, and functions is the term that is used in high level to talk about the same idea, which is subroutines or code reuse or modular programming. So in C, we can define functions which will be translated to subroutines when we convert our high level code into assembly code. The syntax for defining a function in C, basically you put a function name between parentheses, you define or put your input arguments to the function, and curly brackets define the function, the statements, you write your statements of the function, and you define the return value of the function. If your function does not return anything, simply you put void, you write void. If your function returns a character, for example, here, you have to say character, and at the end of the function, you return some variable of this type. For example, if your function returns an integer, you say integer lower to upper, and you return some integer value. So this is very important. You might need to use it in order to write your program in a structured way, in a modular way, where it is clear which function does which task. Few examples here, how to write functions. I will not go through them. I will leave them to you. All of them are not related to the microcontroller. For example, here, write a function to find the square root of 32-bit integer values using the successive approximation method. So this is something related to numerical analysis. It talks of an example on to write a function to do that. Frankly speaking, I don't remember what is successive approximation. I forgot it. But these are just examples to show you how to write functions, the structure of the functions. Another example, test whether 32-bit non-negative integer is a prime. So this is the code to test whether a number is a prime or not. The function is called prime test. It returns an unsigned integer value. Here it returns 0 or 1. 0 or 1. Write a program to find the number of prime numbers between 100 and 1000. So basically here, he did not write a new function. The function that determines whether a number is a prime or not was on the previous slide. So here he wrote a main program, then he wrote a for loop, and inside the for loop, he called the function that is called the prime test in order to test if the number is prime or not. Okay. Sorry. Okay. Another thing that might be useful for you is the header files, where you can define your own header file. You put your definitions and so on if you need. We already used header files when we write include derivative.h in Code Warrior, or derivative.inc, which includes all the equate statements that define the registers and the bits inside these registers for the HCS12 microcontroller. Pointers, as I said, we will not be writing complex C programs. So pointers is considered as an advanced topic. It will not be needed in this course anyway. I will not discuss it, how to define pointers, how to reference and dereference pointers, examples on using pointers. They are not of importance to us. A topic of importance to us is arrays, and we already saw or wrote programs that work with arrays at the assembly level. So we will be doing the same at the C level. So we need to know how to define arrays, and this is probably straightforward for you. In C, you can define an array, one-dimensional array using square brackets, using this syntax, two-dimensional arrays using this syntax. So the syntax for defining arrays is using square brackets. Other languages, they use parentheses. You can define, you need to specify the type of the array. For example, you say integer x10. Integer x10 implies that you are declaring an array with 10 elements of type integer and so on. So here are some examples. Here we're defining integer array called AX that contains 20 elements. This is an array of 20 integers. These statements, they define pointers. They define pointers, which is not of importance to us. Passing arrays to functions, you might need to do this. For example, here, if you define an array in your program and you want to pass it to some function called average. So basically here the array is defined, you pass the array and the function will accept the array, process it, and return some value to you. So this is straightforward. Structures, how to define structures, how to reference structures, the fields, kind of advanced, but if you feel that it will help you in writing your program, please go back and check it. I will not go through it. Unions, same thing. So that was a very quick overview and review on C. You need to practice. You need to lubricate your hands and try to write a few programs in Code Warrior, as we will see shortly. using C. In addition to using assembly, use the simulation. I know that you don't have the board. Simulate your program and try to track the changes in the memory and in the registers as you probably learned during the tutorial. Now, the next topic is basically how to write C programs to perform simple I/O operation. It is very, very straightforward. It was already easy in assembly. Now it is even easier in C. So basically, what we do in C in order to perform input-output operations, simple input-output operation, basically we need to configure the ports and the pins and the corresponding pins, and then we need either to output or to input. So for example, to configure a port B for output, simply we write DDRBFF. This will store a value FF in port B, which makes all pins as output. So basically, we are not writing, when we did that in assembly, we wrote move B hash $FF DDRB. We are no longer writing this. This will be done by the compiler. The compiler will convert this high-level statement into this assembly statement. So we are just storing this value in the DDRB register, which is already defined in the include file as an address. So the compiler knows what value to put here when it converts this statement to assembly language. Same thing in this other line, configure the lower four pins, for input, for output, and the upper four pins for input, import A. Same thing, this is port T, configure it to 0, so only pin number 5 from port T is configured as input. Few examples, the following instructions perform simple. Now this is how to configure. Now how to read, it's very straightforward. When we, for example, if you want to read from port B, we used to say LDAA, for example, PTB in assembly. Now in high level, we just write PTB equals this. This is an output. For example, here PTB or equals 02. So this implies or port B with this mask, then store it in port B. If you want to read from some port, this is how do you do that? You refer to the data register name, then you store it in some variable, which is equivalent to LDAA PTA, for example, or LD whatever register you load it into PT from PTA register. So this is very straightforward, much easier than what we did in the assembly level. Okay. What is the time? Okay, so we are about to, time is about to finish. So let me go to 5. Very quickly to, what is left is just examples. So here example, a C program to send values 0, to send values 0, 0 through FF to port B. So simply, we want to write a program that sends 0, 0 to port B, then 0, 0, then 0, 1, 0, 2, 0, 3, and so on. So it is a for loop that simply outputs a value to port B. So this is the program. This is the way it is done in many IDE. When you create a project in CodeWarrior, and you tell Code Warrior or configure Code Warrior it's going to be a C project, it will include the appropriate file for you. So you don't have to write this if you want to write this program in Code Warrior. Just write the main program. This will be already inserted in your file. So here we have defined some variable, unsigned character Z, DDRBFF, port B is configured as output for Z equals 0 up to 255, Z++, port B equals Z. So we output Z to port B. So we start from 0, then up to 255. 255 is essentially FF in hexadecimal, 255 decimal. Then we do this once. If you look at this program, it's not continuously outputting the values 00 through FF continuously to port B. It will do it once. Once it finishes, it will come here. It says while 1, and the body of the while loop is empty, which means once I'm done outputting the values, the microcontroller will go into endless loop. This is the same thing that we did in assembly when we, at the end of the program, we said we can write something like this: done branch done, if you remember, to prevent the microcontroller from going beyond the end of my program. So this is the same thing done at high level. While one implies while true. So this loop will be always executed. You will never get out of this loop. And basically this loop is empty. You are doing nothing, which is 100% equivalent to this. It will be translated by the compiler to something like this. Now, what if you want this sequence of instructions to be executed forever? You want to output the values 0 through FF forever. What will you do? Simply, you will put this where? Where to put this? Inside the while loop. Yes, Susan. We put it inside the while loop simply. If you remember the examples we did in assembly, if we want to repeat the task over and over, we, at the end of the loop, we branch to the beginning of the loop, not to branch to the same, we don't branch to the same line. Okay. Same thing here, a program. As I said, what is left are simply programs. Output these values, send hex values for ASCII characters, 0 through D. Okay, I can see it. C, yes, through to port B. Nothing new. But we want, here we don't want to send the hexadecimal, we want to send the ASCII. So what he did here, he defined a character, a string, that contains these values. Now, because I defined these as string, each element will be represented in ASCII format. So when you say here, port B equals array my number of Z, index Z, what will be sent is not 0, it will be sent the ASCII code for 0, which is, what's the ASCII code for 0? $30. Next time, I will send the ASCII code for 1, which is $31, and so on. Okay, and this is only done once from Z equals 0 to 10. After that, we go into the endless loop. Okay, this one you can try in Code Warrior, and you can observe the variable Z, and you can observe the variable port B, which refers to the data register of port B. Same thing here, set of programs. All of these are examples. I will come to this topic next time about the time delays in C, how to do that in C. And all of these are examples, how to serialize data, examples to connect, a lot of examples actually. They are not from our textbook, most of them, they are from another book, which is in the reference, among the references in the syllabus. Same example here that we saw in chapter 4, but now it is written in C. Same example written in C. Other examples. Inline assembly. Now, if you decide to write your program in high-level language, sometimes you might find it more suitable to write certain part of your example of your program in assembly. So in your main program in the C using C in C, you can switch to assembly by writing ASM, and then you pass the instructions that you want to execute in assembly or write in assembly as a string. For example, here ASM SWI, ASM CLI. So you can write one instruction per line. So this might be useful if you want to switch occasionally inside your program to assembly. Yes, Z++ mean increment the counter for the loop, of course. Yes. The last, I think, 10 slides is just an overview on how to create projects in Code Warrior for C programs. The slides might use, I think, an older version from the version that you have, but the idea is the same. So it shows you how to create a project in C, how to pick the model, how to choose a C project, and so on, all that stuff, how to do the debugging. And it's kind of straightforward. If you are familiar with any development environment, IDE environment, then using Code Warrior is not a big deal. So please go through these these examples. You don't have to cover them all, but try to read them. Try to write the program before you look at the solution of the example. I don't have to, it will be very hard for us to go through every single example, but most of them are doable. You can go through them. So next time I will just go back and talk about the time delays for a few minutes. Then I will go to chapter 6, which is very important. It talks about interrupts, how to use interrupts in this microcontroller. Okay, so any questions? Okay, how was the quality of the lecture? Was it okay in terms of lagging time? Were there any time lags? Okay, okay. So hopefully this situation will not last too long, but in case it lasted longer than 2 weeks, we can do the lectures over here. But there is one important thing that I wanted to do today was to give you the boards. Unfortunately, I cannot. So let's see how things will go through the coming 2 weeks, and based on that, we decide what to do in terms of the project and the boards. Okay. Now, if you liked the idea, we may do it like frequently. Sometimes we do it online. Sometimes we do it physically. Depends on the situation. Maimuna, it is recorded, so you can go back and check the recording. So now I stopped the recording because we ended the lecture. Do you want to stop recording?